Thank you very much for joining me this morning here. I would like to talk a bit about multimodal corpus linguistics, and first thing maybe to explain why do we actually need to study multimodal language, because let's face it, in corpus linguistics, by default, people study written language, and then there are some courageous ones who actually study spoken language. And the problem is, of course, that language and communication is multimodal, and we can see that if we look at this example here. So this is the written representation, for instance, from automatic speech recognition. I have to excuse, I've used this example before, but I love it so much. It's my favorite one. So if you've seen it before, sorry for that. So, okay, let's just break this down. First of all, I'm not married, I'm married, that's all. Does that make sense? Not at all. Okay, if we listen to it, it becomes slightly better. Okay, something is going on because these two instances of married sounded very different. The first one is twice as long, exactly twice as long as the second. And it has a fully released final stop and all these things. So, but still, it's not 100% clear what's happening. What's happening is it becomes clear from the context if you look at the video. But first of all, maybe even more context here. So Ellen DeGeneres had been accused by some pastor that she's celebrating her, and he was writing that in a Christian Post with quotation marks around marriage, her lesbian marriage on TV, and therefore influences young girls and things like that. And that's where she comes to it and says, I'm not married, I'm married, that's all. And you have no chance of understanding this without the video signal. This adds, in this case, a tremendous amount to the communication. Now, that's not always the case. Very often, the meaning that is added via the gestural channel, basically, is much more subtle, of course. But still, this is a good example of showing why we need to study multimodal communication. Now, where do we get this from? I talked a bit about the data set and how it's accessible at UCLA. And basically, my project, how to turn that into multimodal corpus so we can use it in corpus linguistics. And I'll give you some case studies and explanations then onto. So let's start with the NewsScape and the distributed Little Red Hen Lab. Where does all this data come from? Well, I'm using the UCLA library broadcast NewsScape, which is an archive. So they just collect TV news. They actually started in 1973 with the Watergate hearings. They said, oh, this is so interesting, we need to record this. And they bought tape recorders and recorded it. And then during the 1970s, 80s, 90s, they recorded national TV news and local news on videotapes. This data set I'm currently not using. They transitioned to computer recordings in 2005, 2006. Sorry. Now we lost it. Where does it have my email? Can I just hide this? Yeah, normally I should be able to. But if I can read it. Video. So then I think it's probably this one. No. Maybe because there's something in the chat. Yeah, okay, well then let's close the chat. Exactly. Good morning, that's great. Okay. Normally it disappears like folds up. Exactly. Sorry for the audio chaos this morning as well. Yeah. Can I just move this around? I'll just move it onto my other screen, you see. I don't care about it. I don't care that much here. Yeah. Okay, and then I'll try to stand in front of this microphone. Sorry, if I keep wandering around, you just remind me, please. Can you hear me now in the back? Okay, thank you. Yeah. So the computer recordings is basically when I start using this. Of course, I didn't start in 2006, but that's the data set that I'm using. And from 2012 onwards, they started recording all over the world. Well, in selected places, wherever they could put a little recording station and transfer the data via internet to UCLA. Why can they do that? Because if I did that in Germany, I'd probably be in jail by now. And the reason for this is that Section 108 of the Copyright Act in the United States says an archive is allowed to record television news and lend out copies. Now, you may have guessed that this is not the latest legislation, but it has never changed. This is the current wording. And what lending out copies in the digital age means, nobody knows, and it hasn't been tested in court yet. So what we're doing is basically often snippetizing down to 60 seconds like the Internet Archive does, and then say, this is fair use. So currently, UCLA records roughly 150 shows a day, about 120 of which are in English, mostly US American English, and do annotation on multiple levels. And it's much of the research done by the Distributed Literate Hen Lab is based on the NewsScape corpus. So that's a cooperative of people interested in multimodal communication, working together to create tools and infrastructure. So what does this look like? So NewsScape just decided, because they could, they would develop their own data format. And that means you have to start working with data that looks like this. Now, I know all of you are aspiring corpus linguists and are happy to dig into technical textual data. Well, maybe not, but this one here is relatively simple. It has a header up here where you say, okay, we have the show title, Ellen DeGeneres Show, and collection, communication department, duration, video resolution, language, local broadcast time, and so on. And then you get these columns down here, which are not labeled, but I labeled them for you. So display start time, display end time. This is for the subtitles. So they're recording not only the shows, but also the subtitles that are broadcast with them. So to get a simple, cheap transcript. And this is the start and end time of that subtitle line on the screen. And this one here is the subtitle. So like Mickey Mouse doesn't come out that often, and so on and so on. Now, they also do all sorts of annotations, and that's when it becomes really, really complex. Don't worry about that format. This is one of the things that we try to abstract from to make the whole thing user-friendly for users who just want to use the data but don't care about technical details. So if you want to know, ask me about it. I'm happy to explain. If you don't, that's also a good choice. Just to give you an idea of the wealth of the data, we're talking about in March 2021, this is when I last ran the statistics, it always takes half a day. American English amounted to about 400,000 hours or 2.9 billion words of subtitles. So that is quite good for a corpus. It's not like web scale corpus, but there's video recordings for every single word of this. And that, of course, makes the data explode. And then there is Spanish, French, and so on. You see, it goes down very quickly in terms of size. Spanish is still quite good. And then we have stuff that actually comes without subtitles, but they're still recording it because they think they might be interested in it. And maybe speech recognition will help. So how do you get to this? Well, UCLA offers a range of access options. The first one is called image flow, and I call it the least useful one for linguists, because what this allows you to do is to look at shows. So this is one show, 1 hour of recording. This is another show. This is another show. And you can look at these images. Why would you want to do that? Well, because communication studies scholars are interested in finding image reuse. Like, when do you get the same kind of news on various channels? When do they use the same images of tanks rolling into some desert or whatever? That is the kind of questions they might be interested in. For us as linguists, pretty useless. Then they have a search engine. It's called Edge, and it does what search engines do. It finds matching documents. So you type in a word, and it will give you matching documents, and then you can click on this little thumbnail, and it plays the stuff. It has some advanced search, like you can select channels and shows and date ranges and things like that, but no linguistic annotation whatsoever. So if you want to query for a lemma or part of speech annotation or something like that, doesn't work for you. They have another search engine, Edge 2, which now allows these kinds of things. So you can say, I want to have give and damn within I don't know what, and you can give part of speech information, regular expressions. It's very complex, and unfortunately, it doesn't give you like nice concordances. For every concordance line, you will have to click on one of these results, because again, it's a document search engine. That's what search engines do. It's not a corpus tool. And then they have the command line. This is from their website. So you can say, instead of an open-ended search for the word time, we can also just force just the frame time, and then you do some command on the command line for this frame. Then we look at part of speech annotation and, for instance, the indefinite article followed by an adjective. That's the example that they give. And it's a bit cryptic already, but relatively easy to learn. And when you have these, you can then run an intersect command and get a CSV file out of it. Okay, so I did this. It runs about 2 minutes for 1 day of data. Now, that is not acceptable if you have 15 years of data in there. Or you are very, very patient. And that is why we need something else. And this is where the corpus part comes in. By the way, this is also after you run this for like, I don't know how many days, is when you're going to realize that you actually forget none of your adjectives start with a vowel, because you were looking for and not un. So there's some small issues there and then you wait another, I don't know how many days. So the solution to this is, of course, well known in the corpus linguistics community. You use a corpus manager, something like the sketch engine, or in our case, open source CQPweb. And we can run the same thing. And we say lemma A, and then part of speech, adjective, and time expression equals 1, because in this particular case, we had people studying temporal expressions. So we had a tagger run on the data beforehand that tags time expressions. And if you do that, it also takes 2 minutes, but for 2 billion words. So these are the results then. And you see that even though a few or something like that is not a time expression in itself, it's part of a time expression here, a few minutes and things like that. So that's why it's tagged this way. Okay, how do we get there? And that's basically the whole data processing aspect. I'm going to explain that for those of you who are interested in some of the slightly more technical details, and then we'll go to some applications. So first thing is you need to actually do sentence splitting. We improved that with, the whole thing comes in uppercase. American subtitles come in only uppercase. This is a problem for sentence splitting because normally you look for an uppercase letter after a full stop to find the next sentence. So we had to do some tricks, but we went there, then we extracted text that's not spoken. Because later on, if we're looking for words in the spoken language, the word applause isn't uttered very often. What you see, however, in the subtitles, the word applause occurs very often in square brackets, telling us that that's what's happening on the audio channel, but it's not part of the words we want to study. So we extracted it, put it into the metadata. We used Stanford Core NLP, which is a standard tool for linguistic annotation with part of speech, true case, lemma, named entity recognition, dependency parsing, and so on. And then we used forced alignment. Now, for people working with spoken data, forced alignment is a very, very important tool because it allows you basically give the computer some audio recording and you give it a text file with a transcript and say, hey, can you match these two somehow? And then the computer comes up for every word with start and end time in that audio signal. And how good does that work? Well, overall files, in our case, the tool that we're using, Gentle, reports itself with something like 91.59% success rate. Now, why is it that high or low? Well, the reason is that subtitles are not exact renditions of the spoken words. In American TV, they're actually pretty good. It's not like if you're watching German TV, so German TV or German DVD subtitles or something like that, let me tell you, that's just an abomination. In American TV news, it's relatively good, but still you get normalization, false data are omitted, and sometimes it's too fast and people, there's basically regulations that they only can display a certain number of words per minute, and then they have to shorten what is being said. So there's lots of things happening why this is not an exact transcript. So 91 point something would be good. And we have huge variance, actually. So we have files with 100% error rate. Yes, that happens. Usually it means something went wrong in the recording process. And we have something like recording subtitles for one program, but not for the other, or for 1 hour, and we have a 2-hour recording. So things like that. There are all sorts of weird errors that occur sometimes if you have data at this scale. Also, we have something at 0% that's just as dubious. That can't really happen. Because if you get 0% error, usually, you know, subtitles lag behind. So if you start recording, you're already you're still seeing the subtitles for words that were uttered before you started your recording. And at the end, you have words for which you haven't got the subtitles in your data. So 100% is also wrong. Something is wrong usually means there's just like 1 or 2 words there. Now, we did a manual evaluation of a sample of average files. And for 2016, which is newer data, with slightly better audio quality, Gentle reported 94.1%. And out of those, 93% of the words were correctly lined. So we get about 87.5%. There is other software, the well-known Web Mouse by the Bavarian Archive for Speech Signals, which is great, don't get me wrong, but it doesn't really work well with when the transcript doesn't match the audio. So when you have these problems that I just mentioned, that it's not the same, then it completely fails. But that's why we get such low rates for that. But with 87.5% with that data set, we can live in a way. And then we ran some image annotation. The first round of that was a master's thesis by a guy who now works for Google. And he created basically a tool that gives us things like, is there a person on screen? Is the speaker on screen? Are the hands moving? And it gives us time codes from when to when hands are moving, heads are moving, in which direction, things like that. And again, we have to ask, can we trust it? And the answer is it depends. So if the computer says there's a person on screen, in like 95% at least, the computer is right. So that's good. However, it misses people sometimes, because if somebody is not full frontal, if you're filmed from the side or slightly from behind, then suddenly the computer doesn't necessarily see there's a face. So that's one problem. What is worse is the hands moving annotation. So we basically tried that, gave 200 cases where the computer said hands are moving to human annotator, and said, are the hands really moving? And the human annotator said in about 1/3 of the cases, yes, the computer is right. In about 15% of the cases, the human annotator said, no, they're not moving. And in about half the cases, the human annotator said, there are no hands. And that is worrying for this. That's a problem with this kind of annotation. So we need to improve that. And improving video annotation can be done, for instance, by using a software called OpenPose. And if you're interested in these kinds of things, I take it you probably have already booked James Trujillo's workshop for this afternoon, who's going to explain how to work with computer annotation and manual annotation together. If we go back to our example, what this tool does is basically it tries to get information on your joints and paints them, but also stores them in numeric format for later use. It looks like this. Okay, and we see if we can also just look at the annotation, and we'll see that it sometimes during fast movement, it like loses the fingers. So it's not 100% reliable by far. but it's not bad either. Then we're also adding biometric clustering, which is worryingly good, actually. So this is what it automatically, I mean, we didn't ask it for Hillary Clinton. We just said, hey, you take this data set and give us all the clusters for different people. And this is what it came up with, one cluster. And it's really nice. And we're also now deploying active speaker detection, because it turns out very often you have to throw away stuff that if you're looking through data on TV news, very often you see something like, you hear a nice word, you are interested in, say, my Spanish colleagues did this from beginning to end. And you want to see the gestures that come from beginning to end. Now, the problem is from beginning to end or things like that can be uttered while nobody's on screen. You see a weather map. Great. You just wasted 10 seconds of your life looking at a weather map. Now, for 10 seconds, it doesn't matter all that much. But if you're looking through thousands of examples, then it gets really annoying really quickly. And in order to resolve that, what we do is try to see whether the speaker's on the screen, and there's automatic tools for that. We're using an algorithm by Chow and colleagues. So you saw when it's red, basically person is not talking. When it's green, person is talking. And that can, again, we get that as numbers. And we can then later just search for these things and say, hey, can you give me all the instances of the word when the speaker is visible? And that saves you from throwing away a lot of data or looking at a lot of data. Now, some more technical details here still, representation formats. If you're dealing with these multimodal data at scale, well, you come from a corpus linguistics background, or you're trying to become corpus linguists. So what you're doing is usually you're working with words. You have word indexed annotation. So you have a word, and on that word, you can have a part of speech annotation, you can have a lemma annotation, and whatever. And then it looks something like this. So you can have these tables, for instance, where you have this is the difference between a patriot in 2000 and a narcissist in 2016. And part of speech, lemma annotation, UD relations, these are the dependency relations, named entity recognition, normalized named entity recognition, things like that. So you get the idea. On each word, you can have annotations, and then you can represent it in a table like this, like the Connell format or the vertical format that is often used in corpus linguistics. And if you want to mark certain regions, you can put like XML around it and say, okay, this is intonation unit start, intonation unit end. That is the standard in corpus linguistics. And it doesn't help you much if people gesture, because it turns out they don't gesture exactly on individual words. So what we have, this is an example from Su-Wai Wu's PhD thesis. And we see that in this case, sorry, the annotations are given on certain times. So we see when there is a preparation. So the annotation here says stroke, retraction, stroke, hold, preparation, stroke, hold. So basically preparation is you put your hands up, stroke is you make the gesture, and then hold is what I'm doing now, and retraction is you're going back with your gesture. And this is then analyzed in very great detail by people studying gesture and multimodal communication. And you get these kinds of annotations. And they're not linked at all to the words necessarily. They can be. The same for our automatic annotations here. They just basically look at images and say, hey, are the hands moving or not? Can we see the person or not? And that means we get what is called time-indexed annotation. So instead of saying, hey, we have information of the word, we have information on time slots. And on that time slot, we then have the words. This is the format that's been used by UCLA, for instance. Or if you're using Elan, I think there was a workshop on that yesterday. Is that right? 2 days ago, Monday, whenever. I saw there was a workshop. If you're using that, this is the file format that sits behind it. And it's also time indexed. So what you have is basically you have these time slots in milliseconds, and then you get the kind of annotations, preparation, stroke, hold, and so on. with relation to these time slots that are listed up here. And this format is, of course, much more difficult to query. How do you search in that? How do you find things that co-occur with different words? That's a conceptual problem, that you have two kinds of ways of looking at this data. And our current solution is rather simplistic, but actually powerful enough. And that is, we basically go through this and say, if hands are moving here on these words, and then the hand movement is stopping in the middle of patriot, what we do is we're going to put hands moving as an attribute on this word with 5, 5, 5, 5, 5, 5, 4, 3, 2, 1, 0, 0, 0, 0, and so on. Now, that means you can basically, in your query, say, I want to have a word that is definitely covered by a gesture, or I want to have a word where there's gesturing nearby, because actually gesture researchers tell us that gestures don't necessarily occur exactly on the word, they often occur before, sometimes after. So there is a problem there, and therefore you can say, now give me all the ones with 4 and 3, like at least 1 or 2 words adjacent, and you can adjust that in your queries. That's how we basically annotate this for a very simple way of searching for this. And then we get these weird tables that look like this. And those of you who are going to be in my workshop this afternoon, I'm very briefly going to explain some tables, but don't worry, they're straightforward. So, and then we end up with this kind of thing, CQPweb with multimodal queries. So we can combine annotation levels. We can say, give me the lemma push, word class verb, and I want to have a person on screen and the hands should be moving. And you hit submit, and it comes up with this list. And then you just click on this little TV icon. So, I mean, anything else is like any corpus tool, you know. So it's a concordance, you can click for more context, you can click for metadata, but here, this little TV icon will actually take you to the video snippet roughly 2 seconds before the word push is uttered. So let's try this out. So you can relatively quickly screen a lot of video data, or if you're studying spoken language, a lot of spoken data. Now, there's, of course, all sorts of technical issues. You have to remember that this is done automatically, and there are issues. So you saw the second example with the Joker. What we saw there is that actually the hands weren't moving. Well, they were moving on the screen because they zoomed in on the image. And so the position of the hands on the image changed, and that's what's happening. And you're going to start hating camera movements if you work in this kind of research. So how this helps? This table is actually from a paper that we just submitted to Jespin for another data set. So this is not NewsScape. This is some project-specific data set of Russia Today data. And if you're looking for, we were interested in will uttered by a certain person who's a host, Sophie Shevardnadze, who's a host on this TV show. And if you just look for will with part of speech modal, and you will get 6,700 hits. And if you want to look through them, that takes some time. It's possible, but it takes some time. You can easily reduce that by saying, hey, is Sophie actually visible on the screen? And then you're down to half of that. Now, with a new active speaker detection, so this is basically based on the biometric clustering. So here we add biometric clustering, and then we're down to half of it. Then we add active speaker detection. Is it actually Sophie Coe who's speaking? And can we see her hands? Because sometimes, particularly, this is a show where you actually can see hands, but then COVID hit and they recorded her from her home, like with a webcam. And then suddenly hands are not always visible. So if you do that, then, first of all, if she speaks, you're down to 1,500. And then if you say, can we see the hands? You're down to 985. Compared to 6,700, the amount of time that you save annotating by using these automatic annotations is just tremendous. And if you say, no, that wasn't enough, actually I'm missing stuff that I'd be interested in, then, well, you can actually say, give me that, in this case, only greater than 5. So with the computer, it's only 5% certain there's a hand, not 20% certain. And it's enough if you can see the hands like 2 seconds around will. Why is that important? Because will is often criticized at all, and it's very short. And if you get a hand movement during that, that gives us motion blur, and then we suddenly don't see the hand, and the computer says there's no hand, where there is a hand. So that's why we look 2 seconds to the left and right too, and or we allow for that option to make sure we catch most of the ones that we're interested in. All right. Now that is if you want to do manual annotation, or manual analysis. So you go in, find your data, go through it, annotate it. We have a tool called the Rapid Annotator that helps you classify your data relatively quickly and then analyze it. That's one way. But of course, you might also just want to run data analysis on the entire data set, not necessarily looking at all individual instances that you're analyzing. And that is something that I tried for yes and no. So this was a case study, not so much because I thought I didn't know what's happening, but because I thought I knew what was happening. And that is, I wanted to look at head movements with yes and no to show that my method is working. Now it turns out it's actually more complicated than that. And you don't only get, I was a bit naive, you don't only get yes and no. We'll see that in a minute. So the idea was basically, you could have something like in multimodal linguistics, there's a lot of discussion in construction, grammar, how do we model these things? Is there multimodal constructions? So if so, we would have something like for yes, an affirmative meaning, and then you can have phonological representation yes, or some kind of head nod representation, or both. Is that one construction? Well, that's the main debate here. And I would actually be in favor of saying, no, that's not one construction. We have 2 individual constructions, one affirmative construction that is yes verbally, and one affirmative construction that's nodding. And we know we can use both of them separately, but very often we use them together. We need to model that somehow that we can actually use them together. And I suggest we're using something that is called cross-modal construction. That's a term that I coined to get to work with this phenomenon. Basically, you already learned about collocations, and it's a generalization where you say, okay, can I have a structure or something multimodal occur together with words or other structures or something like that, and calculate their associations. So you would have a Klein like this roughly. So you have things like all the way from CQPweb. This is an example by Elisabeth Ziemer, and she found that in like, I can't remember, it was some weird number, like 90% of the cases, if somebody says all the way from X to Y or something like that on TV, there's a hand gesture. It's really crazy high number. So on the other hand, we have things like air quotes that we just saw. They can occur on any word, on any construction. You can say, hey, how was your summer school in Tartu? Implying that this was all a holiday. And, so anything, there's nothing about summer school that makes you associated with air quotes. Air quotes are completely independent of the items that they occur with, and they're not associated, whereas all the way from CQPweb is very strongly associated to some gesture. And then we have things in the middle here like yes and no. So at the top, we can probably speak of multimodal construction because they're so strongly entrenched together that we will probably retrieve them together, store them together, and so on. On the other hand, here we pretty sure have free combinations where we can add air quotes to anything. And this middle ground is what I'm interested in. That's these cross-modal constructions. So as I said, I'm using here actually a definition of constructions originally by Stefanovic in Greece, but they say, of course, construction analysis always starts with a particular construction and investigates which lexemes are strongly attracted or repelled by a particular slot in the construction. Now you try that with yes and the head nod. What's the slot? What's the word? What's the construction? Now, I think we need to generalize this, and the definition that I propose is the combination of 2 arbitrary constructions on arbitrary levels of representation that occur significantly more frequently together than expected. And with that definition, you can then run actual analysis on the automatic annotation. Now, bear in mind that the data we run this on is annotated by this system that the student wrote. So there are some problems with the data in terms of data distribution. We have much more horizontal head movements than vertical head movements, and there's a whole range of things like that. But it still works surprisingly well with a few caveats. So if we're looking at head moving horizontally, so only horizontally, actually I excluded anything where the computer said it's moving both vertically and horizontally, which is a lot of cases because people sometimes tilt the head and say something like, do something like this. Then the computer says, oh, I found it in both directions. Yeah, right. But for our purposes here, for horizontal head movement, we find pretty much what we expect. So we have attracted no as most strongly in terms of color structure, in terms of color structural strength. Odds ratio not as strongly. We'll explain why in a minute. Then we'll get why in a minute. I'll show you an example. And the other one was which I also have examples but didn't include in this. And then we get the repelled one. The most strongly repelled one is yes. So that actually seems to work quite well. And the looks like this. This is the kind of examples, because I looked at this and was like, why does I wasn't quite sure. I thought it was a hesitation marker. No, it's this one here. And that is very strongly associated actually to the head shake. Now, for head nods, or let's say for vertical head movements, the situation looks different. So again, I mean, the beginning looks really good. The most strongly associated ones are yes, okay, and yeah. So we're happy with that. And then we have and as repelled. Okay, we can live with that. But where is no? Well, no is actually here, and it's attracted to vertical head movement. That was, when I said I was naive, I really was naive. I looked at that and said, nah, I can't be right. Well, it turns out in this case, the computer is right and I was wrong. Because, well, there's two things. Of course, you can agree to somebody and by saying no. So that happens. You don't really think that, do you? No. Well, sometimes you can nod, sometimes you shake. Both exist. We've seen some of that. But more importantly, actually, we have another effect interfering here. And this is why I said vertical head movements. It's not necessarily nods. The problem is why we have all these green things here is that gestures generally tend to be like vertically head gestures when you accentuate things. And that's what happened. Look at this example. You have to say no. And she basically puts that accentuation on, and that is what the computer picks up as a head nod, which is why we get this association. All right. So much for the multimodal, automatic cross-modal color structure analysis. You basically take a lot of data and you run the statistics. The important thing is you go back and check. You look at the examples. It's a typical beginner's mistake to actually report numbers like these without double checking that what's happening is actually what you say is happening. So it's okay to use large data, but you need to draw samples and check. I will say that again at the end just to make sure. All right. There's other stuff you can study with these corpora, not necessarily visual. You can also look at just audio channel. So why is that actually relevant? Well, one major question cognitive linguists like to ask is, how do we store language? And timing information may be an indicator as to whether two otherwise identical forms are stored or processed the same way, whether word combinations are stored or processed as units or individually, and how strong mental associations between words or constructions are. So basically, these whole information about length of forms, of phonetic forms and things like that can give us a better understanding of the organization of the mental lexicon, constructicon, of course. Now, my favorite study about this is actually Bybee and Scheibman, 1999. And I'm just going to summarize it very, very, very briefly. So what they studied is don't. And they saw that repetition conditions, chunking, basically they looked at 138 manually annotated instances of don't. And that is a really nice study, and it got great results, but it's based on 138 instances. That is not a lot. And what they found, and I tried then to replicate that, so I used 415,000 automatically annotated instances, because I had an idea what was going to come out. Again, this was to verify that the method is working. So I went in and said, okay, let's just see what happens if we have don't followed or preceded by certain words. And this is the short summary, because actually this is not the study I want to present. This is the background I want to present. So I don't want to go into the details here, but I basically was able to confirm the hypothesis about the difference between reductions being a frequency rather than a categorical effect, because they didn't have enough data for that. So what you see here, we have on the left-hand side, we have duration of don't in milliseconds, and this is dependent on the preceding word. I, we, you, they, people, investigators. And so there was some discussion in the 1980s there on, is don't shorter because it's preceded by a pronoun, or is don't shorter because it's preceded by something more frequent? And because pronouns are more frequent, is it a frequency effect, or is it a category effect, pronoun versus regular noun? And they didn't have enough data. They basically said, yeah, we can see, we think it's a frequency effect, and we can see it's related to frequency in our data, but the frequency is, of course, because pronouns are more frequent. So we can't see the difference. And with this kind of data, you can actually see that there is a difference within the pronoun category. So that I, which is most frequent in front of don't, actually, and this is if don't is followed by no. So I don't know. And you know, I mean, you know these reductions, I don't know. It becomes very, very short. And so we see that don't is actually shortest, or it's also, this one here tells you how often it's don't, it's 4 segments, or how often it's don't, 3 segments, according to the automatic speech recognition. And again, you see that with I don't know, the t is missing in something like 65% of the cases. Whereas with investigators don't know, there you have investigators don't know in about 75% of the cases, the t is realized. So this is a strong frequency effect, and we have the same thing for following verbs. That's also, as Beiby-Scheibman predicted, basically, that no here has the shortest duration of the d in don't, for instance, if it's followed by no. The problem here is, of course, that if you try to study the last item on that, then the phonetics of the following word will mix things up. So you have assimilations effects of some sort of all sorts. That's why I'm always looking at the part of the word that is removed from the item that I'm interested in to basically get around that problem. Doesn't matter all that much. Just to show, you can basically take automatically annotated data large enough and then get meaningful results out of them that confirm previous theory. Now, the problem is, of course, that we have a really long history of don't know. So how can we be sure that speakers reduce? Is that really a cognitive process? I mean, don't know has been OD founded in 17-something, if I recall it correctly. So maybe we just learn it from our parents, and we don't reduce anything. Could that be true? Well, how do we find out? They could just acquire the reduced versions, but if they reduce due to frequency, can we track such phenomena in real time? Well, usually we don't get frequency changes that often, right? So words don't just explode in frequency. Well, sometimes they do. And I was looking for high frequency combinations that come along quickly and ideally multiple times to see whether there's a pattern. And that's why I decided to take a look into the word president plus the surname. That is a study, again, on NewsScape data. Now in the large data set. Just to jog your memory, American presidential elections, there are some key events. Election day is in November, early November. Then the Electoral College meets in mid-December to basically cast their votes. These votes are tallied in early January, and then you get the inauguration on January 20th. And it's only then that the person is officially called President Biden, Obama, Trump, Bush, whatever. Before that, they're called President-elect Trump or something like that officially, but people already will use these terms sometimes. They will actually very soon say, yes, so we're going to have a President Trump or something like that. And now, let's take a look at how this works. So we have, this is with Obama. The length of the word president in milliseconds when followed by the word Obama in 2008. And what we see is that here, it's hardly used. That is based on 114 data points only. Whereas this whole thing here is based on 71,000 data points. So all the presidents that you're going to see. So we have like 114 data points. Hardly anybody in October 2008 said President Obama. That just didn't exist as a concept or very much. And then once he was elected, it was produced much more frequently, and therefore it became shorter. And then it became shorter, then it became shorter, then it became even shorter, and it stagnated around here. So here it's fully entrenched, I would say. The difference, by the way, between November here and February, March here in milliseconds is about the same difference as the difference of the length of don't in I don't versus people don't. So that's about the same size of effect. So I think we're in a good ballpark here. Now, let's look at Trump. This happens at a different level, but we have the same pattern. It starts here. Now, it turns out a lot of people used President Trump already in 2010, basically to prepare, in 2010, in October 2016. In October 2016, sorry, in the 10th month. So a lot of people already used it here. Why is that? Well, because the channels already ran these like, oh no, we must avoid a President Trump. There can't be such a thing as President Trump and things like that. So these things happened on quite a few of the channels, of course, not on Fox News, but yeah, so same pattern. Let's take a look at the other one that I have, and that's Biden. Something went wrong here. What's going on? Well, the answer is very simple. Joe Biden is the only person out of the three who had been vice president before. And so what we see here is people saying former Vice President Biden. And if you get Vice President Biden, you get 3 unstressed syllables in between. And that makes it shortened. People really don't like 3 unstressed syllables in a row. They will shorten them. And that is why it becomes it's so little here. Now, once he's elected, we can actually get to President Biden, and then it gets entrenched the same way. And by the way, this stabilizes very, very much here. All right, so we basically see that for President Biden, then it's pretty much as expected. And by the way, why is Obama the lowest on this one here? Well, again, because he's the only one starting with an unstressed syllable. So we get President Obama, and therefore we are going to shorten that. And that's why overall it's so much lower. Trump as monosyllabic is up here, and the other one is so much lower. And we can listen to that in real time. So let's play one example. So this sounded, I think, perfectly normal if you just listen to it. Finally, yesterday, President Obama was asked about and so on. I've slowed it down for you to listen because actually this president has 2 syllables, not 3. President Obama. I'll play it again. President Obama is what he's actually saying. But our brains, of course, insert the rest. And it works like that. And now, of course, if you're interested in this kind of thing, you might also ask, does it work the other way around? Does it get longer when they go out of office? And the answer is a bit. Why is that? Well, of course, these people are often still referred to by their title, President Trump, President Obama. They're not officially called that title, but people address them like this. And also entrenchment doesn't just go away, right? Cognitively, you wouldn't expect that to rise like crazy immediately because you have like one alternating form. I mean, there's going to be some blocking there, but some preemption. But overall, this is how it works. And by the way, note how beautiful these two align to the entrenched version. This is 3.5 years earlier. And this is when they go out after 3.5 years in November. And this is when they actually stop being president. And then it should go up. You see, it's not strong, but it's interesting that it doesn't go below this value apparently across over those 4 years. So there's a lower bound to how much you want to shorten this when it's fully entrenched. So we see small but significant differences. They stabilize by March. And I think we can say we have a frequency effect here that may indicate entrenchment. Okay, one more thing, also fully automatic, now again with video, and that is hand position with high-low. Again, how is this relevant? Well, cognitive linguists, they ask, how do we store, process, and understand language? And gesture may be an indicator as to whether so-called dead metaphorical expressions, such as high standard, are mentally tied to a concept of physical height, and thus to our general experience. So this gives us a better understanding of the role of language, and so on and so on. You've seen this before. Now, why is this relevant? Well, because people argue, this whole debate probably about dead metaphor. If you say high unemployment, low unemployment, I mean, there is no physical difference in a way, and they're not piling up, right? But still, this is from a speech by President Obama that Woodin and colleagues actually found and said, okay, we saw that here he says high unemployment, low unemployment, or something like that. And we see that there's a corresponding hand gesture, which might indicate that we think about high unemployment as something higher than about low unemployment. So the metaphor might not be fully dead. And they did some tests on data from the TV archive, and they found that basically if you have something like low number, low standard, and lower the standard, what you get is downwards movement with your hands. Okay. The problem is, of course, that gestures usually are downwards movement. So if you say something and you say, we have a high unemployment. Well, during that high unemployment, my gesture definitely went down. And that's exactly what they struggled with here for high number, high standard. But you see that there is a larger number of upwards movement compared to the low standard, low number. And it only turns around really when you have something that is an action that you can actually play. You can say, raise the standard. And there, it's much more likely that you actually will move your hand upwards. All right, so they looked at that in manual analysis on this TV data, and I thought, well, can we use OpenPose for that? And so let's try. So we got 10,000 occurrences each of low plus noun and high plus noun. I actually excluded high school and high speed because they were everywhere. American TV news is all about high-speed chases on the highways. And so these were they would have amounted for such a large proportion that you don't see anything about high as such. You see something about the compound, and that's what I didn't want to have. So we used OpenPose annotations with key point confidence threshold larger than 20%. And what does that mean? Well, we have this skeleton here from OpenPose, and we then basically defined a set of criteria. So the procedure was the largest person on the screen is determined. Now, this was on data where we didn't have active speaker detection yet. So we basically helped ourselves by saying, hey, usually the largest person on screen is the speaker. That is, of course, not always true, by no means, but it's a good starting point. Then, and often there's only one. Reference point is the average position of the nose. So that is key point 0 here. And reference unit is the distance between the average position of the nose and the average position of the neck key point. Neck key point is this one, number 1. So we're using that to scale, because if you want to know something about hand positions, we can't just look at hand positions on the screen. OpenPose gives you the position on the screen, but if you see me from here, then my hand is going to appear higher than if you see my full body, and lower than if you see my full body, and then the hand is somewhere in the middle. So you need to normalize this data in some way. And then for each visible wrist, the mean vertical distance to the reference point in reference units is calculated. And then only the higher one is used if there are 2 visible wrists, because we expect that people don't necessarily gesture high and low like this, but they may be using one hand or the other. And anything above 3 and below -7 is removed. I'll show why in a second. And yeah, I think that's basically it. And then let's see, where are these hands? So note that I looked for position, for highest position during the utterance of the word low and the no, actually only in the word low, because I didn't add the noun, because then I get a higher chance of getting something higher, because the nouns are of different length, and then I get effects of that sort. So we actually didn't include that. We only looked at low and high, but they needed to be followed by a noun. And this is the results. These are the data points. Now, at first, this may look weird. What does this mean? Well, actually, this is a human scale. So what we have, let's look at my colleague Georg Hager from High Performance Computing at the University of Erlangen-Nuremberg and run OpenPose on him. And if we do that, let's make that a bit more visible and place him on here, we see that we now put his nose on 0. So that is number 0, and his neck key point we put on -1. That is how we scaled these points. So basically, any point that you see here, the average means the average person has their hand roughly here. Okay, that's the mean position of the hand, the vertical position, roughly on this height. And that's also why below -7, how the hell is he going to get his hand there? And above 3, no way, were removed because we could be sure that these are computer errors of some sort. And so comparing these, we actually do see that there is a difference between the two. And the difference, even though it's small, because, well, guess what? Most of the time, people don't gesture and have their hands roughly in this resting position. So that's why we have the bulk of the data around here. But you see that it's a bit more densely populated up here. And it is higher. The difference is, of course, because we have such a huge data set, the difference is highly significant, no question about that. And it works. So with high, we get slightly higher wrist positions than with low. Now, let's compare this with lower and raise as verbs. Let's try the same thing. So the left ones are still the ones that we just saw, low and high. And we see it goes up a bit. And then for the verbs, as predicted by Wooden and colleagues, we actually get generally higher gestures because the verbs attract more gestures. So even if you say lower, your hand is actually going to be somewhere higher because you're moving it. The highest position of your hand is going to be higher than in resting position because you're performing a gesture. But it's, of course, lower than it is for raise. So we see that this actually works out pretty well on the data that is fully automatically annotated with OpenPose and then processed in the way that I just showed. So I think it's time to wrap up. You've given me another minute or so, I think. This is going to be very short. I think what we've seen is that we can speed up certain types of research with the help of the computer, which is what I would call the semi-automatic method. So you ignore all the junk where you have weather maps, outside shots, reaction shots, whatever, and you don't see the speaker. But we also have evidence that the fully automatic methods can be used instead of manual measurements or annotations if we use a big data approach. What does that mean? it means that we have so much data and we make sure that non-systematic errors should cancel each other out, and manual verification, but that still means manual verification of samples is necessary at the beginning to make sure that we don't have any systematic errors in there. And that means always go back to the concordance line. Really, it's important. But if we do that, then it reveals patterns that we cannot see in small data sets, and therefore hopefully can give us better cognitive models of language and communication. I would like to thank you very much for your attention. Of course, I'm absolutely happy to take questions.
Thank you very much, Peter, for a fascinating talk. I never thought that the American presidents would make a significant contribution to cognitive linguistics, but they have. Any questions in the audience? I think we can, have the roaming mics. One is very difficult to turn on. Okay, two here in front.
Thank you very much for this very interesting presentation. I was wondering about the results that you were presented in respect to low and high, and whether we can disentangle whether this metaphor is dead or alive.
We can't. Let me just make this very clear before I start, because one thing, this is really all instances of low and high. So this includes all the physical ones that people talk about. So we didn't, this is not exactly the same. So here, what I wanted to show is basically, if we have enough data, we will still see the signal, even though it's muddied down.
Yes, but in respect to how gesture can inform or give some indication on whether it is dead or alive, and given that you also mentioned that the effect is there, but it is pretty small, I have maybe some hypothesis or why it might be so, especially in respect when you mentioned that even with high unemployment, the gesture you mentioned that tends to go down. But there is an important aspect that we have to differentiate between pragmatic gestures, which have to do with the discourse and with the stress of information, and there are representational or depicting gestures which have to do with the representation of the information. And so when we are talking, let's say, about high and low unemployment, we might stress high, we might stress low in the same way. However, if we are using gesture iconically to represent low unemployment and high unemployment, also indicate linking more to the metaphor of the gesture, then that would give, let's say, maybe would provide cleaner data. And I would assume if there would be a possibility to filter between sort of these pragmatic gestures out, because the iconic ones are the ones that could really indicate whether these terms are conceived as metaphorical in high and low, I would expect that the results that are presented there would be super clear.
I would expect that too, but usually, so thanks, this is absolutely right. So I agree with everything you say. The only problem is that we've tried a bit manual analysis, trying to disentangle what type of gesture things are. And the multifunctionality of these gestures is just crazy. So you have things that look like they're strokes, but they're also pointing at the same time. They're still giving you hand shapes of some sort. And let's just say, I know enough humans, including me, who have trouble, certainly filtering out pragmatic gestures. So there is a certain risk of removing data that you don't like if you do this kind of thing. And I have, given that I think that we as humans have still a lot of trouble making that distinction, or maybe it's not possible because we often get various things at the same time superimposed on one gesture, various functions, that let's just say I don't see any way of automatically filtering these at the moment. But the good thing is, for this kind of question, you can always go back to the semi-automatic method and improve your chances by just throwing away the junk and then looking through instances that you're really interested in.
Perfect, thanks.
Well, thank you so much for that talk. It was absolutely fascinating, and I'm especially interested in multimodal constructions. However, I'm working in language acquisition, so first language acquisition. So I was wondering, these software that you introduced, like OpenPose and so on, they are integrated into the Red Hat corpus, or are these like open source software that you could run other videos on?
OpenPose is completely open source. Everybody can download and run it on whatever they like. It's not related to us. We're just using it. It comes from Carnegie Mellon University. And there is now a whole range of contenders. So depending on what kind of data you have, if you have only one person on screen, Google Media Pipe might also be useful, but that doesn't allow for multiple people on screen. And then you have OpenPose, AlphaPose, DCPose, OpenPIFPath. There's like tons of these. We're trying currently to evaluate how these deal with different kinds of data, but we don't have any results yet because we need to go manually check various types of data for that. But yeah, this is free. And the problem with these is usually that actually installing OpenPose is a pain in the neck. So you need a large server, you need a fast GPU, you need to be able to SSH into the shell and have these run all these commands and compile things, and it's just something that is not very linguist friendly, let's put it that way. So as you saw, we're trying to get things working, and that's also what we're in my workshop this afternoon. What we're doing is basically we're looking at stuff that linguists can use. That means that you can use it with a web browser, because that is usually when things work and when people will use it. Like ChatGPT, the actual breakthrough technologically was GPT-3, which was half a year earlier. It took off when they put a web interface in front of it that actually chatted to people. And then people realized how powerful it was. And so for this purpose, we actually have applied for a grant to implement infrastructure where you upload your video and it is then processed. Now, technologically, I think we can do that. And we will be able to do that, hopefully, if we get the grant, which we will know in August. Then we're trying to set up an infrastructure like this. The problem is that usually your agreements don't cover that. So whether you're legally allowed to upload your data to our server infrastructure is something that we will be working on. So we're currently thinking about producing agreements that basically state that it will be processed by the whatever consortium running servers in Germany using the following the European data protection laws and so on, and so that you can get your experimental subjects to sign this to be absolutely sure, because usually what you have them sign at the moment is that you're only going to process the data at your home university or home institution. And so there's a legal issue here that we have to bear in mind as a community. But technologically, it is no problem if you know how to run this stuff on Linux and have computational powerful hardware, and hopefully soon no problem if you have a web browser.
Okay. Thank you. Looking forward to the workshop.
Any other questions?
Thank you. I wanted to ask about the subtitles. So I understood they are automatically generated. So how accurate are the subtitles? How much can you rely on that information?
Okay, the subtitles in American TV news, most of the data that we have, they're actually not automatically generated. They're generated by people who have something like a core typewriter. And so they're trained to do this relatively quickly. That is up until roughly 2018, 19 maybe. And then more and more of the speech recognition stuff came in. The BBC, on the other hand, for which we don't have much data, they have been using automatic speech recognition for ages, and they have a very clever solution for this, because, you know, training automatic speech recognition on random people is difficult. They have all these weird accents and things. So what they did is they trained speech recognition on specific speakers, put them in a soundproof booth, gave them headphones, and then the speaker is repeating every word they hear, and the software is actually recognizing it. And then they can still like give them the options, and they can select like the second or third if the first one wasn't right. So there's some technology there, and that is moving also to the United States. But for most of the data in the NewsScape corpus is actually manually transcribed, and we see lots of typos and things like that, and transmission errors. But we also have automatic transcription. So the corpus that I mentioned on Russia Today, that we downloaded off YouTube the weekend before it was blocked. So we have to, if anybody wants to study Russian disinformation, I have 20 terabytes of Russia Today. Get in touch with me. This is interesting. And for this, why is this important? First of all, automatic speech recognition, Google is pretty good at that. So YouTube is pretty good at that. And so the YouTube subtitles, for English at least, are of a sensible quality. They're not perfect, but if you, I don't know if you've watched them, YouTube with subtitles on for English language, if the audio quality is good, and that's usually the case in studio recordings, then it's pretty decent. And so we're downloading those and live with the errors. Since then, Whisper has come along, which is an OpenAI's speech recognition model, which is better because it brings basically a large language model with it. So it's like a GPT-like language model. That means, however, it has some really undesirable effects for linguists, and that is that it normalizes data. So it will replace non-standard forms with standard forms. It will just gloss over wrong endings and correct them. It will write what people probably would have said instead what the person actually said. It will completely forget about false starts and all these things that you as a linguist might want to study. Still, it's very useful as a first index. So if you're interested in studying, say, the verb throw, then using Whisper is perfect because it already gives you an indication of roughly where. Also, it doesn't have exact timestamps yet. There's lots of tools that try that, but it's not perfect yet. But if you have Whisper subtitles, then you can just go in and jump to that position of throw roughly, like, okay, 10 seconds before, and then you can look at it. But if you're looking at hesitation phenomena, no chance. Does that?
Yeah, I was just kind of the case with the will right? So how well captured?
It isn't that bad actually. The YouTube subtitles are doing a relatively decent job at getting that. Yeah.
Okay, thank you. Any other questions?
Yeah.
Thank you very much for your presentation. I thought this was a little specific, but since you've mentioned automatic text recognition, I will ask. So I'm actually working on the evaluation of the output from the respeaking process. That's what you were talking about. And I was wondering, you mentioned dental. Do you think it could be used? Has it been used for evaluation, subtitles evaluation also? And I'm not very sure. Like I didn't know dental. I know Whispered. And do you think that a language model could be embedded somehow in dental?
Okay. So I maybe should briefly explain. I left out the technical details in that talk, but so there's two ways of doing forced alignment. And did I understand that you're evaluating speech process, automatic speech recognition output? Okay. On what kind of data? Conference data. Okay, I see. Yeah. So for that thing, Whisper is probably pretty good, but with all the problems that I just mentioned. Gentle comes with an automatic speech recognizer inside that is based on Caldi. Caldi is an open source speech recognition toolkit. And so you can use it. We have tried this. We have used it to force align Whisper output. And that's in principle possible. I have so Gentle uses a language model by choice that only consists of the transcript. So it basically takes the transcript, then runs speech recognition process that uses a very simple bigram model of all the bigrams found in the transcript. Therefore, making sure that, or minimizing the chance of wrong recognitions. And that's the internal way how it deals with this. Now, therefore, I think the idea of adding a large language model to Gentle, I don't see how that should improve things, because the strength of Gentle really is that it tries to match the text and the audio and put them together. If you get in an external language model, then again, you run the greater risk of introducing artifacts that come out of the model instead out of the signal. Does that answer your question?
Any other questions?
Natalia?
Sorry.
Natalia.
Thank you so much for your fascinating talk. So I was interested in phonological reduction, kind of efficiency things, as you know, probably. But I was really curious. If you compare durations of this present plus name across different news channels, like take Fox News or CNN, would there be different results?
That is one of the things that I was thinking about doing, yes, but I haven't come around to doing that yet, because that was exactly my question, whether whether according to political leanings you see them entrench faster, for instance. That would be really interesting. Which, however, it might just be hard to distinguish, because my suspicion is that the frequency will already be higher on the respective channel. And because, you see, president is a term of address that shows a certain type of respect. And so my understanding was that, for instance, Fox News often called President Obama just Obama and avoided the president. But this is a hunch. I have not looked into that, but I would find that very interesting. Yeah. So yeah, let's talk about this, because I have been thinking about that too, whether particularly, I mean, for those of you who are not familiar with the American TV news landscape, there's like, usually people used to say there is CNN, which is sort of neutral. Then you have MSNBC, which is left-leaning. And then you have Fox News, which is somewhere on that door. Right? and the question is, of course, where you're standing, because if you're standing where that radiator is, then CNN is also left-leaning. And so there's a lot of discussion in communication studies and media science about media studies, how these relate. And they use things like that, trying to who addresses whom as what, how often is person mentioned, how often does it collocate with positive, negative terms, and there's lots of interesting stuff to be done. And so the question would be for us, does Fox News as a right-wing outlet show that, for instance, it uses president more often with Trump than with Obama, or that it adopts it faster and entrenches it better, pronounces it more quickly, or we don't know. But I think that would be a fascinating area of research.
You have a question? Okay.
Is this on? Is it working?
I don't think so.
Okay. Thank you for it. Was there are so many interesting studies in your talk. I'm curious, partly because of the research that we're doing in the MEDAL project, about cross-linguistic research in gesture studies. So I would imagine that this kind of comes back to the difference between gestures that are collostructional in a particular language versus gestures that are pragmatic versus gesture. I mean, I imagine there's a huge range of difference of to what extent you get differences between languages depending on whether in a particular culture there, how the meanings are assigned. But how much cross-linguistic work has there been so far in corpus gesture studies? I know it's a new field overall.
I'm probably the wrong person to ask. So I did all this research as part of an English department, and so I focused on English alone. Now, the people to ask are, of course, in this consortium, and particularly I would be thinking about Asli Özurek's group at the MPI, who have looked at these things. And I mean, from my understanding, everybody seems to, so there are some studies about, like, well, guess what we prototypically expected, that Italians gesture more than Scandinavian people or something like that. Yes, that's true. Or Turkish people gesture more. So there have been some studies on that as far as I know, but I'm not aware of like systematic corpus-based studies, but that is me not being aware. Really, that makes a difference to me saying they don't exist. I just wouldn't know. Sorry.
Okay, thank you.
Okay, if there is one last very pressing question, we can have that, and otherwise we can go to the coffee break.